please. My name is Fintan Selby. I'm the team leader and hardware lead. I focus mainly on the RC plane itself, like the structure of it and the flight controller.
I'm Franklin Castillo Mateo. I'm hardware and I focus on the long-range plane communication and parts.
I'm Eliana Montalegre, and I worked on software, and I focused mostly on the mission planner, obtaining flight time data, and using Google Earth and maps.
I'm Miguel Espinal, and my focus was on creating all the simulations on Mission Planner.
This is our project motivation. There's a need for an efficient method of delivery of medical supplies in the underdeveloped areas of the world. Because of the lack of supply or the lack of accessibility in order to receive medical equipment in time, more people are dying than they have to. These deaths could be easily prevented. In related work, in the past, drones were tested when UNICEF set up a drone testing corridor in Malawi in early 2017, where an 80-kilometer radius area was tested by working on humanitarian applications, where drones were used to transport medical equipment. Next slide, please.
This is the related work and originality. The first company to come up with the idea of drone delivery was Amazon. In December of 2013, Jeff Bezos, the CEO of Amazon, announced that Amazon would be started working on drone delivery technology, but they wanted to keep up with competition like Walmart, FedEx, and USPS. So that's why they wanted to start early. But it actually turned out that a company called Wing, a subsidiary of Alphabet, a parent company of Google, first started in the U.S. This year actually, and they're partnered with companies like Walgreens and FedEx, transporting packages and medicine, whatnot, and they're the first U.S. company to get a license, a FFA license to fly unmanned drones here in the United States. And then companies like Zipline, Skyports, and Matternet are all delivering medical supplies. Zipline has the operations in Rwanda. They're delivering blood and plasma to hard to reach areas. They use a launching technology that is used on U.S. carriers, which allow for faster takeoff and less drag because there's no landing gear. And that's what we kind of aimed for our drone. Is we wanted a plane, more or less, not a vertical takeoff drone.
So hospitals and other medical facilities depend on wheeled motor vehicles or pilot aircraft to deliver supplies, which can be slow due to terrain or traffic issues and costly for aircraft delivery. This can lead to hospitals being low on supplies and not being able to treat all patients or respond to any emergency that occurs. Our goal with this project is to present an autonomous drone as a more flexible and fast delivery method that can be used anywhere and by everyone to help medical supplies get to the facilities that need them. Next slide. This is our description of our system. So the system will use Mission Planner as a ground station where users will input the coordinates of the destination where the package needs to be delivered. Once the user has input the coordinates, the Mission Planner will create a path for the plane to follow and send the directions to the plane via map link for the plane to take off to the destination. Once in the air, the plane will use the flight controller to control the motors on the plane to follow the directions it receives, unless the sensors detect an obstacle, at which point the plane will calculate a new direction to move in to avoid the obstacles and then return to the original path that was set for it. Next slide.
This is our related theory. As you can see, the related theory displayed in the picture above shows some of the basic electronics theory that was needed in construction of an internal battery pack that would be able to supply enough power to our drone's hardware and software. Next slide, please.
Along with the rest of the related theory, a big issue that comes with utilizing machinery is the noise and vibration that could interfere with its performance. With unnecessary noise and vibration, it could make your machinery less accurate. So filtering is a process that removes some frequencies from the signal in order to suppress the interfering frequencies and reduce the noise. The first stage that we have is our filtering of the signal using a variable bandwidth Kaiser windowed filter with coefficients such as B1, B2, etc., while the second stage utilizes a low-pass wavelet filter with a variable level of decomposition. We chose this combination because it allows us to control the transition range of the bandpass when using a low-pass filter. The raw signal is passed through the Kaiser windowed low-pass filter and then filtered by the wavelet filter to further suppress the high-frequency noise and smooth the filtered signal. Wavelet filters are capable of providing smooth data for signal reconstruction, whereas the filtering bandwidth for the Kaiser window can be chosen based on the characteristics of the two filters that are combined together to provide one overall filter that is efficient and low frequency attenuation while keeping the filter order minimal, in other words, keeping the delay minimal. Next slide. So as a continuation, as a vibration damping, these are the formulas that we used for the Kaiser windowed low-pass filter and the attenuation level. A1 represents the amplitude of the original signal, and A2 represents the filtered signal. So on the graph on the right, you can see that the blue signal is what we have as our original signal, and then after it went through the filter, it is what the red is right now. So you can obviously see that it has reduced the noise by a lot. Next slide, please. So this is also LiDAR sensors. What are they and how do they work? So LiDAR sensors are great when it comes to object detection. Using the measured time between emitting and receiving the signal, the known speed of light, and the distance between the sensor and the target, we can calculate the LiDAR waveforms in the formula using the formulas above. So if you look at the little clip on the right, essentially, so the sensor emits a pulsed light waves into the surrounding environment. These pulse bounces off the surrounding objects and then return the sensor. So as you can see, like there's a green dot and how the light is bouncing off and returning it. So the sensor uses the time it took for each pulse to return the sensor to calculate the distance it traveled. And the sensors will detect all materials regardless of color, surface. The only exception is wool because it absorbs sound. Also, wavelengths vary to suit the target from about 10 micrometers to approximately like 250 nanometers. Typically, the light is reflected via backscattering. Different types of scattering are used for these different LiDAR application, and the most commonly is Rayleigh scattering, which reflects the particles much smaller than the wavelength. Next slide.
This is the hardware design and implementation. So we decided to use a plane kit for our project. We decided to use the XUAV Clouds plane. This has a wingspan of about 6 feet 2 inches. Its cruising speed can be from 30 to 50 miles per hour depending on the motors, and the payload weight can be around 2 to 4 pounds depending on the battery size, and the average flight time is about 30 to 60 minutes depending on the battery size as well. This is our hardware implementation for the flight controller. The flight controller is the Maytech F405 wing. To the left is the schematic for the wiring, and to the right is how I applied the wiring. The flight controller has an accelerometer and a compass in it, and it allows for the user to understand on the grounds what the position of the plane is in the air. So what I mean by position is like pitch, roll, and yaw, and then it can also record like the acceleration it experiences during flight and whatnot. On the left, you see the ESCs connected, and in order to control them, you need to connect the ground and control wire. And those are servos 1 and 2, and then servos 3 through 9 spots are allocated to the roll, pitch, and yaw servo motors, and then potentially the payload release servo. And then we also have connected a video transmitter and a camera. This allows for the plane to transmit video, and we'll show you video later on in the demonstration. And then we also have a compass, a GPS and an ultrasonic sensor attached to the board as well to give us the exact location of the plane during flight and the also to give us a obstacle avoidance system. This is the battery pack. To the left battery pack is for testing the plane and potentially small test flights, and the right battery pack is longer test flights, like 30 to 60-minute test flights. I mean, not test flights, real flights. And the left battery pack has a voltage of about 14.8, and the total amount of milliamp hours is 3,500. And then the battery pack on the right is 14.8 volts as well, and has a milliamp hour of about 10,500.
This is our firmware design. So we've been working with both DroneKit Python and Adu Pilot. Both of these help us communicate directly with our plane using Mathlink. They allow data logging, analysis, and simulation tools so that we can test our autopilot system. In the algorithm one, we can see that we have a function in that assess the target altitude in centimeters as an argument. It then slowly increases the output of RC channel 3, which is the throttle channel, while continuously monitoring the plane's altitude. Once the target altitude is reached, the function returns. In algorithm 2, we have another function that continuously monitors the plane's altitude and applies slight adjustments to the throttle accordingly. This function is invoked after reaching a target altitude and is executed in a separate thread so that it is always attempting to hold that target altitude. Next slide. So here we have the general setup of our software implementation, where we are in Mission Planner, and a mission has been created for the plane to solid, where each waypoint is a destination where the plane will travel to. Next slide.
So as I mentioned before, there can be effects from vibration that could really decrease the accuracy of your system. So our Adu Pilot has accelerometers that are sensitive to vibrations. These accelerometer values are combined with barometer and GPS data to estimate the vehicle's position. With excessive vibration, the estimate could be thrown off. The goal of vibration damping is to reduce the high and medium frequency vibrations while also allowing low frequency actual board movement to take place within the airframe. Things that can help with these vibrations are foam, gel pads, and 3D printed walls. Here we have an example of what the vibration look like. So vibrations below 30 are normally acceptable. Anything above 30 may have issues, and levels above 60 nearly always have problems with position or altitude hold. Next slide. So here we have our actual data graphs from the vibrations during our flight. So you can notice how the vibration is greater at the beginning and the end due to the takeoff and the landing. Next slide. Here we have more graphs. So it shows throughout the entire duration of the flight. Most activity happens, as I said, in takeoff and landing. So we have acceleration, and it compares the velocity and acceleration due to gravity. The landing compares pitch and altitude. The angular alignment compares the adjustment of the plane when turning. And that's why you can kind of see some activity in the middle, because it's turning to go to the separate waypoints. And then the last one there is for the server for the payload release. It's active in the beginning because we want to make sure it was functioning. And then towards the end, it's active again when we wanted to test the payload release in our software. Next slide. And here we also have our battery monitoring. So a test our battery usage. It also would give us notifications depending on what the battery was currently at throughout the flight. So this just compares like your voltage and your current and what it's being used for. And then on the right, we have Google Earth. So we were able to combine it with Google Earth, and it was able to plot our altitude and the waypoints. So it represents the entire test flight, and it's especially useful because you can see the exact roll and pitch at each selected point in the flight for wherever you choose it. Next slide. So this is our firmware detection. We have our object detection. So we made blue points as a fence to act as a boundary to a certain area. So it can act as a object obstruction when we're testing it from point 1 to point 2. On our right, we have the Max Sonar EZ4 high performance ultrasonic sensor. This one's a narrow beam providing noise resistance tolerance with an average of 10-meter distance. It is not the best. It's just really reasonable for the price. The most ideal is the one I had mentioned before, which is the Lighter 360, because it has a longer range. It's 100 meters and it uses a laser scanner. However, it's really expensive and it usually ranges around like $800. Next slide. So this is an example of our object detection that we also implemented into Mission Planner. On our left, you can see that this was an object and it has a radius around it, around like 10 meters, that it just starts showing off that there's going to be an object and it's going to start rerouting. And on the right, we were able to implement it in MATLAB. And you can see on the right how there's a graph. It's going up and down. It's changing because it's showing the distance the plane is from any certain object. Next slide. So this is our fastest route algorithm, DeCostra's algorithm. This works hand in hand with our object detection. In the following pseudocode algorithm on the right, the code searches for the length of the distance between the two neighboring nodes. This is especially useful when you want to integrate object avoidance. When the object is detected, you then want your system to figure out the fastest route and most effective way around the obstruction. So once it realizes that there is obstruction using the sensor, it then can also work with DeCostra's algorithm, because you want your system to be able to figure out the fastest and most effective way. And if the path is shorter than the current path it's already recorded for, then the current path will replace the alternative path. Next slide.
This is the battery pack testing. When we needed to change batteries halfway through because we realized that the battery pack I was using before had 36 cells, which was too heavy for the plane to take off, and it showed when we tried taking off the plane because our first test flight the plane crashed. But when we made the two new batteries, like I said before, we made two new batteries, and they both should be within the range of 14 volts to 16.5 volts, and they were measuring about 16.4 and then that was the left battery pack, and the right battery pack was measuring at a 14.8. Both were a success, and both work perfectly fine with the motors and the flight controller.
This is our risk analysis and testing. The test cases define exactly what the module must do. The testing prevents future mistakes since the development of the module is complete when its test is passed. Unit testing is a test functionality of the systems in isolation. It includes the fastest route algorithm, damping vibration, and testing of the battery pack. Integration of the testing integration testing means that helps to ensure that requirements are being met while also allowing us to think about extreme cases, such as making sure our sensor is detecting the objects at a rapid rate so that it has time to create a new plan to follow, and that the battery is powering the motors and then communicating with other hardware parts. Our testing helps with our risk analysis because we want to do the most that we can to prevent any complications. We're using a flight simulation to test the software aspect first, to make sure that it's perfected before we try to fly our actual plane. This allows us to avoid any possible issues due to crashing our model and having to rebuild it. We successfully tested all components, and they worked how they were required to. Next slide, please. This is our project schedule. It shows the timeline we had from December to April. It showed in December we designed and ordered parts that were required for the project. In February, we completed the plane kit model. In March, after building the plane kit, we were able to finish the flight software and flash it onto the flight controller. In April is when we started all the tests of the plane. Next slide, please.
This is the project completion future work. The challenges we overcame were I had to learn how to 3D print, and we had to learn how to design 3D models in AutoCAD, and then the software side had to learn how to implement algorithms into the software and upload it to the flight controller, and then the software side also had to learn how to use RG Pilot as well. For future work, we were unable to fly the plane because due to the battery being big for the first one, and then also we were also having malfunctions in takeoff for the second and third and fourth test flights. So we would like to finish flying the plane and potentially releasing a payload in the future, and then improvements that we could make on the project is a custom flight controller with a built-in GPS, which gives us a better, more accurate position on the map, and then we'll replace the servo motors with plastic as the gears, and instead with metal gears instead, so that the gears don't break or skip during flight. And then we'll also want to design a takeoff launch system, kind of like the zip line plane I mentioned before, where it's launched from like a catapult.
This is our cost analysis. As you can see, we went over the budget. The cost of the drone exceeded the limit, but it was needed to efficiently build a drone. The most expensive items you can see above were the X-UAV cloud plane kit and the 40 lithium batteries that were needed to power the drone. Next slide, please.
All right, so this is the project demonstration. I'll show you the hardware part. We were unable to combine the video, so this is why they're separated. So right now, I'm about to show the accelerometer working with the accelerometer compass working with the flight controller. So as you can see, as I move the flight controller, the MAV link is connected, and it shows what the plane would do during flight. So it's yawing at the moment there, and you can see the yaw is changing. The yaw number is changing, and then I pitch up and pitch down, and that shows, and then rolling left and rolling right. So that shows what's happening. And then in this video, I show what the camera sees, and I show how the flight controller is connected to the servo motors. So when the battery's connected and the flight controller is connected to the servo motors in the plane, when I turn to the left, the roll, it will roll to the left, and when I'm turned to the right, it rolls to the right. So the aileron should go in that direction, and same with pitch, and same with yaw as well for the VTAL. And then at any time I want to, I can take control. See that there's a camera, and then at any point I can take control of the plane by moving any of the sticks during flight. So I'm taking control by rolling the plane to the left and right, and then also the pitch as well. So I'll just end it there. And then here's the software with the waypoints. This is the drone had taken off, and it's going to the plane is taken off from the airport, and it's flying from each waypoint, and shows the battery voltage as well. This is all simulation, of course. We never got to actually fly the plane, sadly. So yeah, there it is, and then you can see that it started rolling to the left there, and it's going on to the next waypoint. So we want to finish this up. So that's, and then it'll also auto lands, and then we can also set points for the drone or the plane to release the payload anytime it wants to. All right, so
this is our code, standards, and restraints. The picture above, you can see it's one of the FFA regulations they established back in 2016. The semi-autonomous drone was planning on flying below the max height of 400 feet. We plan on programming a low flying route. And then currently, the FAA regulations currently limit the cruising height of drones and require line of sight control. So it's fully autonomous drones have to fly higher than the limit and would certainly fly beyond the line of sight of the operator. So the FFA is working on expanding drone permitting, and several tests with autonomous drones are underway. Next slide, please.
This is the code of ethics that we have followed and made sure that we didn't break any of the rules here while we were creating our project. Next slide.
This is the engineering complexity of the project. technical issues. We wanted to reduce the complexity of the project in some way. So in the future, we could make the product more user friendly, which might mean making it easier to launch. Because at the moment, you have to launch from your hand, and then we can also make it easier to charge. We can have a charging board connected to the battery instead of a balanced charging lead, which makes the charging slower. And then the multiple disciplines that we used were all computer and electrical engineering disciplines. So we had to use the aerospace engineering discipline a lot in this project because it was the use of aerodynamics and whatnot. And here's our references. And that's it. Thank you for listening. And any questions?
Okay, thank you so much.
Yeah.
We're going to